Good evening, all of you. Let's see if someone else is joining or not. We are 5. I'm not sure if there will be other people joining in, so we can start. As said, we would focus on chapters 11 and 12 today at first. So if anyone has any questions, please feel free to ask.
Professor, do you mind if I ask you a question by my voice rather than chatting?
That's fine.
In the chapter 12, it's about the uncertainty analysis, and in the 28th slide, there's an explanation about cumulative distribution function.
Yes.
And it says it's about the probability that the output is smaller or equal to certain value y.
Yes.
But I believe that the value of y is quite critical in this defining the uncertainty of the output. So is there any criteria that I can know, at least know if certain probability meets this value, we can say that
you have to check for every value. So your actually y might be not the best choice here for a letter. Let's say we have or I can keep it y, doesn't matter. So let's say we have a random variable y,
yes,
which can take on certain values. Then f of y, so the cumulative distribution function for the value y, so this y now is a real one, capital Y is a random variable. So I think here it would have been better that this is capital Y and this is small y. But basically, this is by definition the probability that my random variable is smaller or equal than this y. And as you see on the graph, to get your cumulative distribution function, you have to look at all possible outcomes. So you still have to find the curve over the entire range to get the cumulative distribution function. So you don't have to make a choice at this moment for determining the CDF. You just have to do it for every or for all of them.
Oh, I see. And as an additional question, in the 41st slide, you mentioned that that the larger sample size can decrease the uncertainty.
Mhm.
And I found that this is quite similar. This has quite similar figure as the CDF. So like I just want to know how the CDF works for decreasing the uncertainty. In other words, decreasing the variance of the output.
Not. The CDF has nothing to do with it. So here if you look at the x-axis, so what you are plotting is indeed the probability to be smaller than the x value. So these are the CDFs that you are plotting. But the fact that it's decreasing the variance is just, let's take this one. Is just because what you now see is that the width here becomes smaller. But the CDF is just an example on which we showed it here. I made a plot for the CDF, and you see that there is more variation in the different CDFs of the Monte Carlo analysis with a small sample size than there is with a large sample size.
Yes.
But it's in that way. So if I increase my sample size, then we see on this plot that the variation decreases. But it would have been the same if you would have taken another function normally. So this is just an example for a function, but CDF does not directly relate to sample size or to variation.
Oh, I see. I thought those two figures had similar structure, so I thought they were.
No, it is indeed a CDF, but it was just to show that the variation decreases.
So it's just the characteristics of CDF, right? The larger sample size decreases uncertainty.
Well, no, the larger sample size decreases the uncertainty for your different values. And the way to illustrate them is, for example, through a CDF or through different CDFs here. Or you could also take the CCDF, then you would have the opposite plots and they would go like this. Or if you have another representation of your distribution, you would just see that the variation would decrease. But you are right that normally the most common visualization is through CDF or through CCDF.
Oh, now I understand. Thank you.
Okay. Yeah. Good. Then there was another question on chapter 11. I'll copy this one to everyone. So if you send the question directly to me, I'm the only one who can see it, so I've copied it. So chapter 11, page 6, I cannot understand what transform the value back to the same random itself means. Okay. Yeah, I see what you mean. No, if you take random sampling, what I meant there is if you take random sampling, you take a random value between 0 and 1 on the x-axis, the y-axis, sorry, on the probabilities. So you pick a random value here. So the first one was this. The first one was this one. But you are not interested in the value of the probability, but you are interested in the value of the random variable. So the random variable here was a triangular one, which is on the x-axis. So you have this curve is your cumulative distribution function. So what you have to do is, once you have sampled on the y-axis, you have to find the value of the random variable itself. So what you do is you just bring it back using your cumulative distribution function. So you look for the x value, the v value in this case, the value of the triangular distribution, which corresponds to this probability. And that's this one. So it's 6 point something, which corresponds to the x value for this one, 6 point something. And then the same on the other one, you had a uniform distribution. You take again a random probability. The first one was 0.63. You transform it back to find the value of the random variable itself, was also 6 point something. And then this gives you this. So you take a random probability. So you always do the random sampling on the probability for the V distribution. You check which is the value of the random variable that corresponds to it. This gives me the first coordinate, so the coordinate for V. This gives me the coordinate for U. So this, saying this and not showing it is sometimes difficult. So this is the one for U. This is the one for V. And then you combine those. So this is the U value. And this is the V value that you found here. And then you combine those to find a random, a bivariate random variable which is composed of U and V. Is this more clear? Good. And then I'll do the same. So I think I'm the only one who sees Yuju's question again. So let's copy and paste. It's a, so it's based on this. So you have a forward difference, a backward difference, which you can sort of see as a left limit and a right limit. If you just think in calculus, you have the right limit is coming from the right. So this is with values larger, which corresponds to the forward difference. Here you also have values which are larger than the other one, and you look at the difference and you divide. The backward difference, you have values smaller. So this is sort of the left limit. And saying that the backward difference and the forward difference have to be the same is actually, it's intuitively the same as saying that your left limit and your right limit have to be the same for the limit. The reason we choose those to be equal is just to find a unique perturbation factor, an optimal perturbation factor. So there needs to be a way to determine which perturbation factor to use, which psi to use. And so we have to find a way to do it, and that's the reasoning behind it. So yes, actually it's that there will be less deviation because you set them equal. So your approximation from the left, your approximation from the right, they will be the same. Good. Any other questions? You can ask about the project. I'm not sure if I can answer it, but you can ask. I have no clue. Not by heart. So the answer model for the project, you had, I think you had a model with 2 interaction terms, I think, before adding the species. And then that one was significant, but then some others became insignificant. Can I find it somewhere easily? Let's see. I don't have the latest version, so I don't have the exact answer, but where is it? Step 4, step 6. Interactions. So you had, if I'm correct, the height, the length, So width, height, and length 2. And then the interaction length 2 with height and length 2 with width. That was the, if I'm correct, the model before adding species. And then you add species, which seems to be significant, if I am correct. But when you add that one, you also see that your interaction terms become insignificant. So you would take those out one by one, and then I don't have the final answer here. So, but the model before species was width, height, and length 2, with an interaction length 2 and height, and length 2 and width. And then you add species, species goes in, and at least one of the interaction factors, but probably both go out. The final project, a couple of days before the exam. So I finished it. I'm waiting for the groups to be finished as well. So there are still 8 people who have to select a group. If not, I'll assign them to a group. But I think that, what did I? Schedule. So normally there is a handout for the project in the week of the 17th. And then the hand in for the project is around the 14th of June. So you have a small month, but normally it's a shorter project that goes relatively quick. But it will be in the page itself. Any other questions? You can. No, the order is important. So if you put the questions, please put them to everyone. It's easier. So when building a linear model, we add the term that is most significant. The order is important, but when we add a new term, it changes previous p-value to insignificant. We delete the previous. The order is important because depending on the order, it will or will not be deleted. Well, it will or will not be included. So the order will be important in adding. So you can, yeah, there is no guarantee that if you add term 1 that, well, if you say I have variable 1, I add variable 2, variable 1 becomes insignificant. But if you have a large set of variables, you have 10 variables, you add the first one, you have, let's do it this way. It's easier to show probably than just to write it. No. You still see the screen, right? Because I lost my visuals. Yeah. Okay. So if you have a model X1 and you have 10 variables, and let's say that all of them are significant, but X1 is the most significant as X10 is the least significant, what you would do is you add X1 and then you check X1 plus X2 plus X3 and so on. And then you select which one to add. If I now say I add X2, then it can be that you just go through a different path. So if you have X1, it might be that you now select X1 plus X3. You might then in the next step add x4, and then you stop because nothing else is significant anymore. It can be that if you start with x2, the next, if you look at the combination x2 plus something else, the next one that you add might be x5, because in this setting, this seems more significant. And then you add, for example, x1, and you end up with x1, x2, x5. The other one, you have x1, x3, x4. So the order is important. If there are very little variables, then most of the time you will sort of end up with the same model. But the more variables you have, the more interaction there might be between the variables and correlation. And so the model that you end up with might change depending on how you start. So it's really important to keep the order and to do it in order of significance. Well, it depends if it's for prediction, yes. So is it correct? So please send your questions so everyone can read them. So the question is it correct to say that one model is better than the other if multiple correlation coefficient is higher? The multiple correlation coefficient just gives the probability, the percentage of the variance that is explained by the model. So a higher multiple correlation is good for a better prediction. So yes, it's correct to say that one model seems better than the other if the multiple correlation is higher, at least if you are aiming for prediction, not explainability, which we are usually doing in our case. But it doesn't mean that it's significantly higher. So if I add more variables, my R² value will always go up because I include more information. But it doesn't mean that my more complex model is significantly different from my previous model. So I could have a model with 2 variables and an R² of 96%. And then I have a model with 5 variables and my R² goes up to 97%. In that case, adding those 3 variables will probably not have a significant effect. So you can keep the smaller model. That's why you have the ANOVA test to check if there is a significant difference between models. If that answers the question. Anything else? No other questions? If not, then we can conclude this session. So Negin is now working on the correction of the project, on project 2. But she has some other things to finish as well, so it might take a week or 2. But she corrects them, I will check them, and then we will get the scores back to you as soon as possible. And then project 3 will be handed out next week once I did a final check of it, and then you can start that one. You will have, yeah, as I said, to somewhere at the beginning of your exam session, because during the exams anyway, you will have to focus on the exams themselves, so it's better to have the project out of the way. But as said, also, it's a relatively easy project, the third one. So you can quite directly apply everything that you've seen during the classes. Then for next week, I will also set a Q&A session for the final 2 chapters, which probably will be around the same time as this one, but I will also confirm that through Euphora. And then if there is nothing else, I just wish all of you a happy or a fine evening and a nice week. I suppose the weather in Korea is better than the weather here, so I would say enjoy the time before the exams are starting. Okay. See you. Wait. Through the river example, I have a question if nonlinearity should be avoided. You cannot always avoid nonlinearity, but you know that approximations, they are best for linearity in the parameters. So you have the model, there is nonlinearity in it, so you will have to make do with it, but you should keep in mind that it is nonlinear, and so that the approximation might not be the best one. But we didn't see any other techniques, so there's not much you can do with what we have seen. So there is the check for nonlinearity in the example, but it's just a check to show how it's done and how you can get it out. But yeah, we have seen those methods and they are linear approximations, and you just have to keep in mind that they are not ideal in this situation. Good. Perfect. Then I'll see you next week. Have a nice day, everyone. Have a nice week, and enjoy Korean Spring for me as well.